got a little microphone here. Is that effective? Are you?
That's great.
That's good. Okay, great. So I'm delighted to be here. I think the last time I was in this room was 2 years ago when I was here with my younger son at new student orientation. So my younger son is a theater major here in Missoula, and I've had the opportunity to come back quite frequently, and I always enjoy it very much. So thanks for the invitation to come and give me a chance to visit again. So today, in the time available, because I assume nobody here is an electrical engineer. Is that a good assumption?
Just you.
Just me. And it probably shows. And I always say when you're a geek, leave no doubt. But anyway, so I'll be talking a little bit about the background of acoustics and audio and what that is about, and then in particular with the project that we've been working on. But I also want to do that because I'm hopeful that some of you out here may have work that you're doing in ecosystem biology, ecosystem dynamics, and whatever that might have the advantage of some knowledge about signals and acoustics and so forth. So if anything comes up in what I say where you think to yourself, gee, that's interesting, that reminds me of, I hope that you'll let me know either today or at some other time about that, because I'm always delighted to learn new things, and that's part of the Ecosystem Institute idea. So I hope that that will work out fine. So I've got kind of a formal outline here of the things that I'll want to cover. The first part will be, as I said, will be about sound and soundscapes and acoustics. And then I'll describe some of the work that I've done over the last few years on long-term acoustical acquisition. And by that I mean making audio recordings that are last days or weeks, or in one case an entire year. So we have an 8,700 hour MP3 file of a recording of a National Historic Site. So those are the sorts of things no one will ever listen to, because it would literally take a year, 24 hours a day to hear it all. So a lot of the work has to be automated search and analysis of those types of signals. Now I'll talk a little bit about the research prospects and then some conclusions if there's time. So to start with, I guess rather than me doing all the talking here, I'm going to give you an assignment, and it's actually going to take a few minutes. So I hope you're ready for that. So what I'm going to do is play several minutes of a sound file, and what I want you to do, or I'd like you to do, is to listen deliberately. And what that means is a little differently than our normal listening. And in this case, I want you to attend to this sound and try to determine the soundscape components. Are you familiar with the term soundscape? What that's referring to is, if you think of a landscape, that's your visual scene. You can see the different objects and animals and trees and plants and the geology and the meteorology and so forth. A soundscape is the analogous view, except instead of using your eyes, you're using your ears. So it's all of the things that allows us to tell what are the sound sources and some information about our acoustical surroundings. So the recording that I'm going to play has a variety of components, and some of those are biological sounds. Bird calls would be an example. Some of them are meteorological sounds, wind, rain, thunder, those kinds of things. Geologic sounds would include water flowing and so forth. And then there are human sounds, sounds attributable to human activity. And these are the sorts of things that our ears and brain are very good at, and we do innately, most of us, from the time that we're infants all the way up, and we don't really think about it a whole lot. It just sort of happens automatically. Okay, so I'm going to play the sound here, and this will be several minutes, so you can fall asleep if you want, or try to see what you hear. Okay, was that summer or winter? Summer? What biological sounds did you notice? Birds? Horse? Did you hear the fly go zzz past the microphone at one point? Okay. Any other biological sounds? Human voices? Okay. What about meteorological sounds? Thunder? Ah, you notice the rain, the little pitter-pat sound is rain? Okay. Any other sound? Do you hear any wind? A little bit? Okay. And other human sounds? You heard some human voices. What other anthropogenic sounds were in there? Train? Yeah, it sounds like the low-frequency drivers must be off in this room. There is a lot of low-frequency energy when the train goes by in the actual recording. Nevertheless, you could tell it was a train, and you heard the train whistle at one point and things like that. Okay, so that's something that all of us with average or normal hearing are able to do pretty casually with our brain, and part of the problem is trying to stay focused on this. I'm sure what was happening is your mind was starting to think about gee, this is going on a long time, and I've got other things I should be doing, and I'm getting a little drowsy. And so you can imagine the grad students that we employ to listen to these long-term recordings for hours on end, trying to keep them awake is a real problem, because listening to something like that, which many people would say that was natural quiet, that was silence. And the point, of course, is it's not silent. There's all kinds of information there all the time that are being used in a natural scene. And then the big challenge is, if I asked you, how did you know it was rain? Can you write down in words what method you used to determine that those were raindrops? It becomes very difficult, because it's something that we do internally, and it's not something we consciously think about an algorithm. But for engineers, if we are going to write computer software that is able to take a 6-minute segment like that and do what we were able to do just trivially recounting all the things we heard, we're nowhere near that. Okay? So there's no systems out there that could do anywhere near what you were able to do just now listening to it. And that's the fun of the research aspect of this, is to try to get automated systems that could do that kind of comparison. Okay, so what is sound? Sound you can think of in a couple different ways. One is vibration of air particles. And so in the room that we have air around us, I am phonating, I'm making vibrations of the air over near me, and those next to them and the ones next to them and so forth, and then that is propagating out through the room. So the particles over here don't arrive at your ear. It's the vibration, the energy that's conveyed through the air that makes it there. Much like dominoes tipping over, the domino tipping will occur over a long distance, but the dominoes near where I am don't actually, move anywhere. They just do a very small motion. The other way we can think about sound is a fluctuation in air pressure. So because of gravity, we've got all this air in the atmosphere being forced down against the ground, and there's a natural pressure all around us. That's what you hear about when there's a high pressure system or a low pressure system in meteorology. So we're used to that fixed pressure, and sound is a slight little fluctuation above and below that ambient pressure, and that's what our eardrum is able to pick up. Behind our eardrum, we have some trapped air in the middle ear that's at the natural pressure, and if the air pressure outside is a little higher or a little lower, then your eardrum moves in or out in response to that. And if you go up in an airplane or drive in a car up or down a hill, you may notice the sense of your ear popping, and that's air being forced in your eustachian tube from your throat in and out into the middle ear to balance that pressure. So the sensation of sound is that variation that we have in there. And then sound is a wave, which means we can measure it from place to place, and we can talk about its characteristics in a wave format. And the relationship that we'll often be using is this one at the bottom here, C equals F lambda. And what that is saying is C, the speed of sound, is given as the product of its frequency times wavelength. So if we increase the frequency, the wavelength gets shorter, so that when we multiply them, we get a constant, which is the speed of sound. So low frequency sound has a long wavelength, high frequency sound has a short wavelength. Okay? And that's the wave behavior. Sound in the air at room temperature travels at approximately 343 meters per second. So that's pretty fast, a little over 700 miles an hour is the speed of sound. Getting that in terms that we can usually think of, 1,000th of a second, a millisecond, sound travels about a foot. So that's about 1 millisecond of sound. And the other rule of thumb is it's about 5 seconds per mile. So when you're outdoors and you see a flash of lightning and everybody starts counting, 1,001, 1,002, and then you hear the thunder, if you get to 5, that means that lightning was 5 counts, 5 seconds away, which is 1 mile. So a lot of people think it's, a mile per second, but no, you got to get to 5 to be a mile. So if you see a flash of lightning and hear the thunder within a fraction of a second, it's pretty darn close, and that's time to go inside. So if you can remember 5 seconds per mile, that's good. You can tell your family that tonight when you get home. Sound in helium, on the other hand, instead of being 343 meters per second, is a little over 1,000 meters per second. And you've all been to a party or something where people inhale helium and then talk, and it sounds weird. And it's because the speed of sound is different in helium, and so you get different resonant characteristics because of that C equals F lambda characteristic. So for a given frequency, the wavelength is different when the speed of sound is different. And by comparison, the speed of light is about 3 times 10 to the 8th meters per second. So light is roughly 1,000,000 times faster than sound. And that's why we can usually, when we see a flash of lightning, we neglect the time it took for the light to reach our eyes. That'll be a 1,000,000th of the time that it took the sound to cover that distance. In water, the speed of sound at 20 degrees is about 1481 meters per second, or about 4.3 times what it is in air. So the speed of sound underwater is a lot faster than it is in the air, and that has some implications that we'll talk about a little later. Another interesting aspect about the speed of sound is it varies with temperature. Speed of sound in air doesn't vary very much with pressure, but it varies quite a bit with temperature. So on a cold day, it is slower than on a hot day. And we usually don't notice that, except if you play a wind instrument in a marching band and it's a very cold football game, it sounds a little out of tune, and it's because the wavelength and the length of the tubing in the instrument is now not correct for a given frequency because the speed has changed. And so you can get some weird effects like that. The other place you notice the difference in speed of sound is if there are temperature gradients in the atmosphere. So for instance, you've probably all been out on a really cold day, and it sounds like the sound is really crisp and you can really hear things a long way away and so forth. And it's because near the surface of the Earth, where the air is coldest, the sound is moving slower. And as you get up in the atmosphere, it's warmer in those circumstances, and the sound is moving faster. So sound from a distance that's coming at you actually bends downward. So the faster speed at elevation causes the sound to refract down toward the surface. And so you end up being able to hear things more effectively at a distance. And then you've probably had the opposite effect on a really hot day where the surface of the ground is very, very hot and it gets cooler as you go up. In that case, the sound bends upward. And so you may have had the circumstance where you're at a place where you can hear traffic very clearly on a cold day, and on a hot day you can't hear it at all, and vice versa. And it's because of this refraction effect. So the change in sound speed that is noticeable there is just like the way light bends in a lens or bends going from the air into the water, that you have a difference in speed of light in those two media, and it also causes focusing. So that can lead to some very interesting effects at great distances. One of the ways that we often look at sound is using a special kind of graph called a spectrogram. And a spectrogram is a graph that on the horizontal axis here is time. So it's early time over there, and time runs along to the right. And then vertically on this spectrogram graph is frequency. So near the bottom, this is low frequencies, bass notes. And then as you go up toward the top of the graph, it gets to be the very high frequencies. And so the colors in here are indicating the relative amount of energy at a particular time at a particular frequency. And so as those change, that's indicating that the sound is changing. And looking at this, anybody recognize what sound this is? Okay, good guess. It's actually speech. And the way we might be able to tell that is, you notice there's all these little parallel lines running along. Those are indicating harmonic sounds. And when people say ah, e, o, u, and so forth, we're generating a periodic pulse of air, and that will show up in the spectrogram as being harmonics. So if you've heard the term harmonics before, that's what we mean, is all of those parallel connections there. And so something like this, if we listen to what it sounds like.
In the course of a December tour in Yorkshire.
So it's a British dude, and he's saying, in the course of a December tour in Yorkshire. And so that is the way that that utterance looks in the spectrographic form. And during the vowel sounds, we get that effect that is the parallel lines, and wherever the words start and stop, or there's a boundary like a k, those kinds of sounds, then we get a slightly different characteristic. And so looking at a simple sentence like that, you can see there's a whole bunch of information here and a whole bunch of detail that we would need to be able to understand. And this is what our brain and ear are doing completely effortlessly when we listen to that segment of speech. So our ear is picking up the signal, the cochlea and the nerves and so forth are getting this spectrographic representation, and then our brain is interpreting that speech very easily. But trying to go from this point to actually describing that can be very challenging. And we'll see, if you look at something like that recording that we heard at the beginning with bird sounds and trains and everything else in it, it's even more complicated than something like this. And looking at that spectrogram, if we look at the different frequency regions, I'm going to play a quick example here of some different portions of that. We're going to listen to the portion of that speech that's below 400 hertz. So this is, those of you that are musicians, it's about an A, the A above middle C and below. This is what that sounds like.
In the case of the December tour in Yorkshire, I rode for a long distance in one of the public coaches.
So, was that intelligible? Could you, sort of. It sounds like Charlie Brown's teacher on the old Peanuts thing. So the energy of the information below 400 hertz isn't really enough to understand the speech. On the other hand, if we listen to the very high end, the portion above 4 kilohertz, so that's all of the fricative stuff in there. But if we listen to the portion that's between 400 hertz and 4 kilohertz, what's left?
In the course of a December tour in Yorkshire, I rode for a long distance in one of the public coaches.
So that portion, which is telephone speech, so you listen on a mobile phone or a telephone, basically what's being conveyed over the line is the 400 hertz to 4 kilohertz. It's intelligible. You can recognize what's being said. You can often tell who it is that's talking, but you're leaving out lots of information. And so one of, again, our challenges when we're looking at sound analysis is to determine which of the frequency ranges are important and how do we make use of those. And the engineers who developed telephones back 100 years ago, part of what they did was to figure out what is the minimum amount of information that's effective at conveying speech, and that's all we're going to send because it's expensive to send additional information. You wouldn't want to listen to high-quality entertainment audio through a telephone. There are other ways to do that, but for speech, it's good enough. Okay, so let's turn from kind of the science of sound a little bit to this concept of soundscapes. And the way that often we think of a soundscape in a natural area or an area that is of interest for analysis is in terms of 3 components. And those 3 components include the biophony. That's the biological sounds that I was mentioning. So those are the things that are animals communicating for mating purposes or identifying their territory or for whatever reason they need to communicate. The geophony, which would be the geological, hydrological, and meteorological sounds. And then we have the anthrophony, the sounds that are attributable to human activity. In some situations, people who are going to a wilderness area and want to have an experience without human involvement may think of the anthrophony as being noise. They may not want to hear an airplane fly over if they're out in the Grand Canyon hiking around. They want to have it just be all natural sound. On the other hand, there may be some visitors to the Grand Canyon who want to fly in a tour aircraft and have a really stunning view of the canyon overhead. And you can obviously see that those 2 activities, while they're both legitimate uses of the national parks, would be an example where there would be a conflict. So you'd have different individuals wanting different type of characteristics there. And so this is one of the soundscape studies and one of the soundscape analysis sorts of things that can be done. One of the projects that I've worked on was a study of the soundscape at the Grant-Kohrs Ranch National Historic Site. Some of you have been down to Deer Lodge and at least been by there or seen the sign for it. So it's a working cattle ranch, and in 1977 Congress started this as a cultural site. So it's not supposed to be a natural site. It's supposed to recognize the ranching heritage of that part of the state of Montana. And so the people that go there are expecting to see ranch operations and hear cattle and all that kind of thing. So the anthrophony, or the sounds of human activity, is actually part of the cultural experience, just like it would be if you went to a national historic battle site or something like that. It was a different circumstance than if you went to a wilderness area. So the managers of the site were interested in finding out what was the soundscape at this site. What did it sound like, and what were its characteristics and so forth. So there's a variety of historic and contemporary sites going on there. The ranch personnel are not dressed in historic garb, so they are wearing modern clothing, and they're driving tractors and so on. So it's not like colonial Williamsburg or something where they're portraying the period. Nevertheless, they do have some historic locations there. So what was done was that we set up a long-term collection site, and we deployed this March 17th of 2009 on a snowy, cold St. Patrick's Day. And at the site, we would have a recording system consisting of a microphone and a sound level meter, which is measuring the sound energy, and an MP3 recorder that was going to make a continuous audio recording. And along with that was a anemometer that was measuring the wind speed, because one of the big problems with audio recording is wind. You've, I'm sure, had the experience of wind blowing over a microphone. It's extremely turbulent, and you get a lot of noise from that isn't really attributable to sound sources. It's just due to the wind. So part of this was to collect the wind speed so we would know which segments of the recording might be contaminated by the wind sound. And so this site had a photovoltaic panel that kept a battery charged for all the equipment. And fortunately nowadays you can get large flash memory chips that can record for weeks at a time. And so we could get about a month's worth of data between visits, 24 hours a day, just constant recording. And so throughout the year we'd go back and retrieve the data and then continue. So we have the 1 full year of data, and in the analysis of this, the biophony that is present at that site is primarily birds and livestock, as you might imagine. There is continuous sound of Interstate 90. Every second of the recording for a whole year, you can hear highway noise. So that's an important thing for the managers at the site to know, that that's part of their natural soundscape in 2009 and 2010. There were also a lot of freight train activity, because during this period they were moving soil from the Milltown Dam site back to Anaconda and dumping it, and so those locomotives and trains were going by several times a day. So that is something that's probably different now than it was that year. And then we had a lot of trouble. It's Montana, so the wind is always a problem at these sites, and so that's something for future research. This is a spectrogram of one day. It happens to be May 4th, 2009, at that particular site, and that's midnight up in the left-hand corner, 1 a.m. over here, 2 a.m., 3 a.m., and so forth, all the way down through the day. And the white marks on there indicating when there is sound at a particular frequency at a particular time. These big white blobs that you see there, that's a train going by. And if you look very carefully up there at the 04 line, you notice there's kind of a dark band across the top. And you see in the 05, there's also kind of a dark band. But now if you look over at 06 and 07, you're starting to see little squiggly stuff up at the top of that little frame. Are you seeing those little wiggles up there? Any guess what that is? No. Freeway traffic is kind of this overall white whoosh that's through there. The sun is coming up, and the birds do a dawn chorus. They start talking, and you can see them start talking there in that 06, about halfway across. Suddenly up in the high frequencies, you see all the little Twitter tweets and so on. And they will continue on, and that's all the way through there up until sometime after 9, almost 10. Then they go out and start foraging, and they stop talking for a while. So it's those kinds of things from the soundscape that we can come up with some interesting biological studies if we know what to look for or listen for or whatever in the sound. And that's just one day, and so there's 365 of these to pore over, literally. Okay, so that brings me to the Sound of Rivers project. And Mark introduced me, and I appreciate that. Thank you. One of the thoughts here, I've done all this work with sound in the air, and when I heard about this possibility that rivers make sound, of course, I'm thinking of the sound that you hear above the water, the riffling sound of streams and so forth. And I discovered that what Mark and his colleagues were interested in was the sound below the water. What is the sound in the water of these streams? And I'm not an expert in this at all, but I'm learning about it. And one of the things that's of interest is the bed load, the sand and gravel and cobbles and so forth that's being pushed along by the flow of a stream, especially at high volume. And then the various other kinds of material that's being moved along in the river system. And the interesting thing is that this varies depending on where you are in the river, what the depth of the river is, what the materials are, and so forth. And so having the ability to use acoustics to try to monitor these things sounds like a really interesting prospect. And along with the putting microphones in the water, and when you do that, they're called hydrophones. So using hydrophones underwater to measure the sound can be done. And then we're also working with this interesting sensor technology with a fiber optic cable that's been buried in the stream bed. And the technology uses flexing of that fiber cable to be demodulated into sound. And the very, very subtle flexing is due to the sound waves propagating through the soil. And so you can pick up those very, very subtle changes. And so the thought is you might be able to have a cable buried near a river and use that as a way to measure a lot of these interesting things like the bed load and the stream load and so forth as it's happening. So in addition to the hydrophones or the underwater microphones, there's also a device called an acoustic Doppler profiler, which is using sonar pulses through the water. And the Doppler aspect is that if those pulses of sound encounter moving material, the reflections that come back from those movements have a Doppler shift, or the frequency is changed slightly. And that same technique is used in Doppler radar to get wind speed in the air. And it's also the effect that you're familiar with of a moving sound source having a there's a pitch change as the sound moves by. There's also the possibility that sound in the air, or the air acoustics, will be of interest to this type of project. And then I've mentioned the fiber sensor as another aspect of this. Okay, so there's a setup that we had at the site up by the NIAC, measuring the air acoustics. And here's Mark piloting a raft with a couple colleagues there, and the device is the ADP. Is that correct, Mark, in the water? Okay. And there's also some hydrophones you can't see. They're small little units that are in the water. And you can see the different riffles and changes as it's going along. And so by listening to the river, then the expectation is we can derive some of these other pieces of information. Here's the sound from a hydrophone that was on that raft near where it was put in. Okay, what does that sound like to you? If you were imagining what underwater might make a sound like that. Sounds like rain. Sounds like rice rolling along in a box or something. But it's presumably the little pebbles and rocks and so forth on the bottom of the river that are being pushed along by the flow. And so as they're tipping over and hitting one another, there's this little telltale sound. Here's a sound at a different site in the river, a little farther down. So at that particular site, there's more high frequency, more of a hiss kind of sound. What is that caused by? Well, maybe there's more sand being driven along. Maybe the flow is different. So those are the research questions which are trying to coordinate or correlate that sound with the physical phenomena. And if we can do that, obviously there's differences in the sound, and if we can attribute those to different physical quantities, then that's going to be a very interesting development for a lot of different reasons. And so knowing that in different places along the river at different times of year and so forth is where we're headed with this. And I'm real excited about trying to dig into this stuff. Meanwhile, here's what it sounds like from the raft. So above the surface there, we're mostly hearing the sound of the oars, the boat itself bumping along. You can hear some of the wind. There's highway noise and things like that. Certain areas along this, and I don't have a recording of it, people on the raft actually could hear the cobbles moving on the bottom of the river. So there was enough energy there, sound energy, that you could hear it from the boat. Presumably it's coming up through the bottom or something like that and being coupled into the air where you can hear it. Let me see. I'm going to skip ahead here. One of the sounds that was picked up at this site happened to be an individual had gone out to do some target shooting, and there's a gunshot here, and it was one of the side interests that I have is gunshot acoustics, and I'll just play this little segment. It wasn't very exciting, was it? Can you tell where the gunshot was in that? Can you tell where the bird calls are in that? If you look along the top up there, there's a real dark patch along the edge, but you'll see little light-colored little scribbles. Let me play it again, and you can hear those where the bird calls are. One of the interesting aspects of this is that there's the gunshot as the top arrow, and then the other little marks there, those are echoes. So the gunshot, the muzzle blast of the gun went off, and then nearby reflections occurred. So at the microphone, we picked up the direct sound, and then those reflections from nearby obstacles and so forth. This was probably about a half a kilometer or so from where the gun was being fired. And the microphone is right at the cabin near the Nyack River. In the air, right. And we'd be interested to know whether that was picked up by the fiber system, and so that would be something for us to go back and look at. The reason I'm showing this, two things. One is that we could see those birds up there. The other is that after the gunshot, the birds were quiet for several seconds before they picked up again. So they clearly reacted to the fact that there had been an unexpected sound, and this is one of the biological interests that we might have, is the behavior of animals in response to human activity and so forth. So all in all here, I think that the conclusion would be that the basic data collection process and observing this collection works pretty well. We can use a lot of the techniques that have been developed for the long-term analysis of air acoustics. There are some issues with calibration, which means determining how big a signal we get from a sensor due to a particular loudness of sound or any of its other characteristics. For air acoustics, we have this wind issue. For underwater acoustics, similarly, we have other turbulence issues to deal with. And then, in general, we have the challenge of any kind of data collection, which is maintaining the site and getting things set up in a way that's useful. So that concludes the remarks that I had today, and I'm happy to take any questions that you might have. First, I'd just like to thank a few folks. The Grant-Kohrs Ranch work, all the staff at that site were extremely helpful, and the National Park Service Program Office in Fort Collins, which is now the Night Skies and Natural Sounds Program, so they deal with both dark sky issues and then also the sounds and so forth. And then the Institute on Ecosystems has helped this. Kathy Whitlock, I think I spelled her name wrong, isn't it? A C-A-T-H-Y? Okay, sorry about that, Kathy. She's not here. I'll fix that before Wednesday.
On Wednesday, right?
Yeah. And Rick, again, thank you for your support of this, and then Mark and the other team members for the Sound of Rivers work. And I'm looking forward to continuing that, and we'll see if we can get some funding to do more of this type of analysis. Okay, thanks very much for your attention.